Example 1. Given a cantilever beam subjected to a concentrated load, we wish to determine the deflection under the load. That is, how much the beam deflects at point A. Assume the beam has a constant EI. First, draw the moment diagram for the beam. Then, draw the M over EI diagram. Now draw the conjugate beam. Load the conjugate beam with the M over EI diagram. Since bending moment diagram is defined as a negative region, the diagram is drawn below the x-axis. We treat the M over EI diagram as a downward load. Now, find the bending moment at A. Here, all we have to do is to calculate the moment reaction at the fixed support. Bending moment at A is negative P L cubed over 3 EI. So deflection at A is negative P L cubed over 3 EI. The negative sign indicates a downward deflection.
Example 2. Suppose we have a beam consisting of two segments. One segment having a moment of inertia of I, and the other segment having a moment of inertia of 2I. The beam is subjected to a concentrated load at the free end. We wish to determine deflection of the beam at the middle of segment AB. Assume a constant E. First, let's draw the beam's moment diagram. Construct the M over EI diagram. Since the moment of inertia for the left segment is twice as that of the right segment, the M over EI diagram is going to look like this. Now draw the conjugate beam. The beam has a roller support at A, an internal hinge at B, and a fixed support at C. Place the M over EI diagram on the conjugate beam as a load. Now find internal bending moment at point D. This represents the real beam's deflection at that point. Let's start by partially analyzing the beam. I say partially because we really do not need to determine the reactions at C or the internal shear at B in order to calculate bending moment at D. All we need is the reaction at A. AY equals 25 over 3 EI. To find bending moment at D, cut the beam at D, draw the free body diagram of the left segment, then use the equilibrium equations to determine the unknowns. Deflection at D is positive 125 over 4 EI. The positive sign indicates that the beam bends upward in segment AB. It's worth mentioning that the conjugate beam method enables us to calculate slope and deflection at a point rather quickly when the beam is subjected to concentrated loads only. When a beam is not subjected to any distributed loads, its moment diagram is going to remain linear throughout. This means we can easily calculate the area under the M over EI diagram without needing to resort to integration, as was mentioned above. However, moment diagram becomes nonlinear if the beam is subjected to a distributed load. This means we actually need to derive an algebraic equation for bending moment, and then use the integration to calculate slope and deflection. Here's an example illustrating this process.
Given a simply supported beam subjected to a uniformly distributed load, we wish to determine deflection at the midpoint of the beam. Let's assume a constant EI. The support reactions for the beam are WL over 2. We can draw the shear and moment diagrams rather quickly without needing to write any equations. But this moment diagram is of little use since I cannot accurately calculate the area under it without having its equation. So let's derive the beam's bending moment equation. Then, the M over EI diagram can be written as, here is the conjugate beam. Here is the beam subject to the M over EI diagram. We need to calculate the support reactions in order to determine bending moment at the midpoint of the conjugate beam. Here are the equilibrium equations. In this case, we can simplify the solution by noting the symmetrical nature of the problem. That is, AY equals to BY equals to half of the integral of the load function. Therefore, AY equals BY equals negative WL cubed over 24 EI. Now to find bending moment at the midpoint of the conjugate beam, cut the beam at midpoint and apply the equilibrium equations to the left segment, like this. Therefore, deflection at the midpoint of the beam is downward with a magnitude of 5 WL to the power 4, divided by 384 EI. See if you can solve the following problems.